Yes, it's been told I'm going to talk about decision trees. Sorry, this stopped working for a reason. Yeah. Problems of being live. Apologize about that. OK, it's working now. Sorry. So, what I want you to take away from this talk basically is my experience on decision trees. I don't come from an academic background. I've been working with decision trees for a while. And my idea after studying decision trees at university was a little bit that was kind of a loser compared to super vector machines and deep learning. It was a model that we had to study, but I didn't expect to use it in real life for real problems. And I did. And my experience, I don't know if anyone has this same feeling of decision trees not being as cool as super vector machines or other models. But if you do, this talk is about this, about how basically you can use decision trees for real life problems. It really focused on classification because it's the problem I was solving. Decision trees can be used for other things. We will also see them, but the experience I can share with you is mostly about classification, so it will be really focused on that. A little bit about myself. I've been a Python user for more than 10 years, a data scientist for a few only. This is mostly my background. I've been working with decision trees for a while, mostly on digital marketing problems. I used to work in a travel agency trying to compete with Booking. That they are here, it's really tough. Don't try it. And well, I'm currently working at Bank of America. If you've been here on David's talk before, one of the banksters that he mentioned. So let's start with an example. I like to organize geek parties, OK? And I like to provide pizza and beers. So basically, there is many people who mail me telling me, OK, I'm coming to your party, but at the end, many people is not showing up. So I have this problem of predicting how many people it would be on these parties to make sure that I don't end up eating cold pizza for a whole week after the event. All what I ask about the people who want to come is their age and the distance from their place to my place. OK, and I basically got some historical information on past events. So it's nothing really fancy, it's just a data set, 2 variables. It's really simple to make sure that we don't need to take a lot of time understanding the example and we can focus on decision trees. OK, if we visualize the data, basically that's what we get. This is, I guess everybody knows Bokeh. If you don't, it's pretty cool library for plotting. Different approaches to matplotlib. You are not making charge scatter or bar charts or anything like that. You are just plotting drawings like circles, lines. So it's really powerful in the way that you can plot whatever you want without constraints or without predefined charts. So what we got here, the red dots is people who really came to the parties. The blue points are people who said they were coming, but they finally didn't. OK. And first analysis we can make from it is like the farther the people it's coming, the less likely they are to come, which makes kind of sense. And there is also a pattern, probably like younger people is not coming as much as older people. It's just some data. So we will start. I assume that most of the people would know linear models better than decision trees. So let's see just shortly how a linear model would perform on that. This is just some code that trains a logistic regression without any parameters, with all the default parameters of scikit-learn. And it's just plotting on the same plot. It's plotting the decision boundary. So this is what we get. It's kind of a really nice estimate, actually, because the two variables are somehow correlated. The separator is pretty cool. Probably if you use a linear supervector machine in this case, the decision boundary would look a little bit better, like leaving some larger margins. So how is a model for a linear model? It's basically a linear equation, nothing really fancy. This is the exact for this specific case. We have the distance, the age with parameters, and an intercept. And basically, we compute this line. Whatever is on one side of the line, so the computation we make is greater than 0, it comes to one of the categories. In this case, the people who is coming, and in the other case, it's people who doesn't come. Sorry. So now same thing with a decision tree, also from the scikit-learn library. And this card plot is not included in scikit-learn. As far as I know, it's something I implemented, and because at some point you will have the slides, I guess, on the PyData website, or if not, you can find me on Twitter, or I'll publish it everywhere. This card plot function is defined at the end on the appendix, so you have the code. So in case you want to play afterwards with the code of the talk, you can do the same things. So basically, we get our classifier, what it's doing. So basically, we have this data, and instead of it starts plotting a line, but in this case, it doesn't capture the correlation between the variables. It always splits just in one of the axes. So basically, the first thing the decision tree would do is just check for the best split of this data, the best possible split, constrained to be only splitting in one of the variables. So before we had this model that basically was capturing everything, decision trees does by parts, one variable at a time. Okay, after this one, in this case, this is the best split. We will see in detail later what a best split means. So basically, in this case, this is trying to split. In this area, is getting what it's mostly called a pure node. It's measuring purity. It's trying to spot areas, subsets of the spaces or areas in the chart, subsets in the data, trying to find like the more pure classes. It means that it's trying to split in a way that in one of the sides, basically, it's getting just one of the classes. In this case, Meta quite a good job in this case, even if it's kind of a, let's call it old layer or someone who didn't show up and was expected, but for the rest is doing a great job. We can see that it's still some work to do in the other side, so it's more or less what we were mentioning before. People come more, basically, if they live closer than 2 kilometers, and of people who live far away, it's like people over 40 is coming more than people under 40. That could make kind of sense. Maybe people over 40 is more likely to have a car, whatever. So decision tree would still go on, splitting all our data, and splitting, and splitting, and splitting more. It will end up just splitting as much as required to make sure that all the nodes are pure. So in each of the knowledge for a classification problem, basically it's saying, okay, if you are trying to predict an attendee who is in this area, basically because everyone did attend in this area, basically is what we are gonna predict. Okay, that's a decision tree, just splitting all our area, one variable at a time, just making sure that we know in each area which are the classes. Okay, that's the model. What does the model look like? This is the representation. There are two different representations, one in Python code. This is not how scikit-learn or any other library would do because they are generic. But if we implement this by hand, this is the function. It's just a list of nested ifs. A list of nested ifs, one for each condition. Each if, basically, it's one split that represents one of the lines that we saw before. Okay, so if we see here, we start checking. The first line is, OK, the distance is smaller than 2.2 kilometers. OK, then we go to another area. We will go on splitting until at the end, you see, the leaf nodes always have only data of one of the classes. This is basically the same. It's checking for each node, and at the end, it's returning the class, whether they will attend or not. It's quite a simple model. So now we'll see some of the properties, what's good, what's bad about these decision trees. First, overfitting. I guess every one of you just realized after seeing this that this is not really a good model. This is not generalizing at all. It's a clear overfit of the data. There is, of course, some decisions that make sense. This case, it's, of course, something that we don't really want to fit our model to say, OK, if there is this one between 55 to 57, even if he lives really close to my place, they are not going to come. I mean, I think it's something that doesn't make any sense. It's something that we don't really want our model to do. So regarding overfitting, what can we do? There are several properties that address this problem. We need to limit the number of splits at the end in one way or another. Okay. The one that I was using the most, the one that was giving more results, and I think it's quite intuitive to understand and quite nice to play with, is this, the min samples leaf. Basically, it grants that at the end of the training, each of the splits you made have a minimum number of samples. So we cannot have the classes where this guy was used by themselves because he's something special. This is something that is not generalized. So at some point, we can say, for example, we want at least four samples on each of the splits. So we get a model that looks probably much better, this one. There are other properties. There is the min samples split, which is really similar, but in another way. In the literature, in academic literature, they like it much more than the min samples leaf. It's basically the same, but instead of granting the number of leaves in each of the splits, in each of the leaves, is making sure that it doesn't split an area, it doesn't split one of the nodes unless there is a minimum sample, a minimum amount of samples. The results are quite similar. They are not really different from what we will get on the min samples leaf. The thing is that if in this case, for example, we had this one was the blue and this one was the red, it could still split. Maybe if we say the minimum split must be 4. So at the end, it could still create a split with just 1. So it's still avoiding overfitting, but in a different way. The max depth, it's also the same thing. It just says that you cannot go on growing like crazy. At some point, it stills. In this case, could be 3. Like we have like three levels of depth. It's like it's not splitting when a split has already been splitted three times, to say, or any time we want. And then we can also limit by the number of leaves. In each of the cases, we get slightly different trees, but in all cases, they will prevent overfitting. So regarding performance, as we've seen before, the linear models basically just compute a linear equation, which for a computer, especially if you are predicting many samples at a time, it's quite easy. It's just a matrix multiplication. Computers are really good at it. So basically what we have is that a linear model, a logistic regression, plain logistic regression, at the end is orders of magnitudes faster than a decision tree. Decision trees is still quite a good model. First thing is that I don't think, depending if the problem is linearly separable, for sure you need to use a logistic regression. If it's not, you will probably end up using a multi-layer perceptron, a support vector machine, or any other model that it's not linear. So logistic regression would be much faster because it's just doing this matrix multiplication. So at the end, it's a bad comparison for a decision tree against a logistic regression, but it's not that bad in the way that if the problem is not linearly separable, we're not going to use that. At some point, at least, we are going to transform the data. In my experience, all the preprocessing was taking more time than the predictions for what we were doing. So I don't think it's a problem, but still, I mean, doing all this for the computer, and besides, this is implemented in a loop in any of the implementations. Probably if you have a tree that it's not that big, and usually trees are not that huge, even if we have millions of data and many variables. So if you implement this, probably the performance is much better, but if you're using scikit-learn, it's somehow slower, even if it's still quite quick. That will depend, of course, on the problem. As I said, it's not the same just trying a decision tree, predict 10,000 samples at a time, that just making them one by one, because the matrix multiplication can optimize a lot if we are predicting a lot of samples at a time. So regarding standardization or normalization, just making sure that all our variables have mean 0 and standard deviation 1, that it's something required by many models. There are many models that don't behave the way we expect and are really biased towards the variables with more variance. Decision trees are not affected. At some point, as you can see, it doesn't matter if we're measuring the distance in meters, kilometers, in miles, or in whatever we want. The split would be exactly the same. And even if you are used to do standardization and you do, because it's kind of a standard, I wouldn't recommend it, because at the end, one of the beautiful things of decision trees is being able to understand the model, being able to analyze what it's doing, why it's doing that. And if we have the original units, a unit that makes sense for us, at the end it will be much easier just to make sure that the tree is the one it needs to be. Feature selection. Feature selection is something that, again, some models require, especially linear models. If you have a logistic regression and you add 10 variables, 20 variables that are pure noise, that doesn't add anything to our model, basically our final logistic regression would be really corrupted. It would be really affected by this noise, and the classifier would be a different classifier. It would be something really different. And probably by different, I mean worse. It would get pretty much a wrong classifier affected by this noise. Decision trees are doing the feature selection in the way that on first node, every time we can compute one of the splits, what we are doing is just analyzing each of the features and trying and finding the split on all the features that mostly creates pure nodes, as we've seen before. So trying to find the variables that discriminate the most. So at the end, if we have just noise, if we start adding variables that are just noise, that don't add any value to our model, at no point on the training of the decision tree, those variables will be used. They will still be noise. Maybe if you have a model that really grows a lot, but as we've seen before, we shouldn't be doing that because of the overfitting. So at some point, we won't end up with a case that these variables are using if we limit the number of samples that we require on each node. Also, scikit-learn can give us a measure of the importance of each of the features, which is pretty useful, especially we'll see that afterwards, that it's quite useful to know what the model is doing, because at the end, if the model doesn't make sense, a model easy as a decision tree doesn't make sense, it's probably that we're doing something wrong. There is something wrong in our data, we are overfitting, there is something that we're unaware. So I think decision trees, something really useful is just letting you understand. In my whole experience, we were spending a lot of time just checking up decision trees and making sure that everything made sense. If there is something that it goes against your common sense, it's probably something wrong on your data. You might end up finding patterns that you didn't expect to find. But in this case, as we saw, the higher the distance is the more likely that a person doesn't show up, or the age, maybe it's a little bit more difficult, but yeah, at the end, just checking that the features are used in a way that we would expect is something I strongly recommend. So feature extraction, data cleaning in general, just whatever we need to provide the model before it can classify. My experience, and I read this several times in posts about data scientists, in many comments, it's like usually much more important to have good data than better models. I mean, we have deep learning, we have super vector machines. In some cases, there are these models that provide really, really good value, but for many problems, the problem we have that we don't have better accuracies is basically because the data is noisy, we don't have the right variables. So at some point, we need to take care of this, and decision trees is not helping. It's something that doesn't take care. It takes care of feature selection and normalization, to say, as we've seen before, but it doesn't take care of that. So yeah, in this case, for example, we could see here's taking the distance, it's taking the age. I was mentioning before, it's like maybe there is a relation on the people coming, whether they have a car or not. It's a variable that we could extract. It's maybe not that obvious. It's not something that we get for granted. But at some point, if we can start crossing data saying, OK, just people over 18 who lives closer to my place is the ones that are really come, because the people younger than 18 that are living far, probably they need to use public transport or something like that. So it's a variable that at some point can be still interesting. It's like trying to predict whether someone will end up using public transport in this problem. Of course, for different problems, it's easier or it's harder to just find the features to extract. But I think it's really useful. And in decision trees, it's much more important, because at the end, as we've seen, we cannot split the data for what we want. As in a linear model, as we've seen, the decision boundary is plotted, finding the correlation among the variables. But with decision trees, it's just finding the splits of one variable at a time. So at the end, if we can more or less capture these correlations, and we can provide with a new feature that basically is making this split much easier for this feature, we can capture much more of the discrimination power just with the first split, which will make our model much better. OK, categorical variables and missing values. The theory of decision tree says that it can process both things. There is no problem for that. The thing is that implementation, scikit-learn as an example, usually don't delete this way, mostly for performance reasons, is the way they are developed. So the approach to decision trees is insensitive. You can keep the missing data. You can keep the categorical variables. In this case, when we want to use a library because our data requires it, if we have 1 million of rows, we're not able to provide, to implement our own solution, because it will be too slow. We need to implement something, I mean, like scikit-learn. It's implemented in Cython. It's optimized. It controls whether the matrix is sparse or not, or our data is sparse or not. So it's quite interesting. In categorical variables, basically, one of the important things is that if they have some sort of ordering, we should keep it, because at the end, the data would be split in that. It would be split in the way that we provide. So if we have a categorical variable that is young people, middle age, and old people, if we keep this order, basically it will be able to group in one of the splits young people with middle age or middle age with old people. Well, if we mix the order, then we have problems. Binding, that's a really interesting thing because decision trees suffer from a kind of bias regarding the highly branching attributes. Here in this example, I changed the age by the sex. We just have 2 sex in general, depends, but. And what we find here is that all the splits are done in the distance because it's the probability of finding a split in the distance better than the only split that we could do in the sex is much, much higher. So at the end, we should try to avoid to have these variables with many, many different values and some others with just few values. We should try to get all our continuous variables in bins. So at the end, they are grouped in different classes, so the decision tree cannot get crazy and start splitting for the same variable 10,000 times. If we can use our common sense to know which are the splits, that's much better. I mean, if there is any point when we want the decision tree to split in that point, I think it's good to give. Unbalanced data. All the literature says, it's surely true, that it's biased toward, the decision tree is biased toward the dominant class. For my experience, that's probably true, but I think it's much less than with linear models. I think linear models are much worse, as we can see here in the example, and it is not that extreme, but as more points we have in this area, this separator basically tries to get away from the dominant class and forgets about the other, is what it's doing, is how logistic regression in this case is performing. While the decision tree still tries to focus more on the class with less elements. One of the properties I was mentioning before is the model debugging. I think if you are using decision trees, and it's probably one of the reasons to use them, is that at the end, when you have a prediction that you somehow disagree, and in real cases, I would say in most of the problems, you know cases when you were predicting something and it was wrong. Decision trees let you debug it. It means that you can just take this sample, this guy who didn't show up in my party and it was expected, and we can just check which exact path followed in the tree. So at some point, we know exactly where were the reasons for it being classified in a certain way. So knowing this basically lets us make the tree better. It can show us that we are overfitting when we thought that we couldn't, or any other reason. Maybe we are missing some variables that they were useful. There is really a lot of information that we can use. Regarding stability, one of the problems, if we have a linear model like a logistic regression and we start changing few elements, the chances that we get that we end up with a really different model are not high. The model will be affected, but just in a small way. While in decision trees, imagine that just few samples make that the first split is not this one on the distance, but it's one on the age. We'll get a total different model. So the stability, even you get few more samples, you train your model again that was performing great yesterday, and maybe your model starts to perform quite poorly or in a different way. That's something that in a decision tree is much likely. Of course, it depends on the number of samples. Then we have random forests. You surely know it even better probably than decision trees come to that. It's an ensemble method that randomizes the creation of a decision tree. And basically what it provides is better accuracy and better stability at some point, because you are just considering some of the variables. At some point, it will make sure that it's combining different trees that split from different points of the first nodes. So more or less, all the possible trees that we could change from one to the other in case of small changes in the samples are there in the decision in the random forest, are one. So just changing few data shouldn't affect that much the model. So now we'll see just briefly how we train a decision tree. It's some theory. I don't know if any of you have did that before, but But the theory on training is just getting a best split. Okay, for each split, basically it gets all the data for that split. It just filters a split. Basically means a feature and a value. It's like distance 2.2 kilometers. Okay, so it gets all the values on one side of this split and in the other. So all the people in this case that lives closer to 2.2 kilometers or higher, it gets them. It makes sure that the split is not already poor. If it's pure, it stops, it finished, it knows what to predict in this point. And if it's not, it just creates another tree in this branch of the tree. So it's kind of it's a recursive algorithm, as we can see. Okay, so as you can see, all the complexity on this is basically getting the best split. How we get the best split? Okay, we take, in this case, the age, but what it would do in reality is just start on one variable and just iterate over all them. And at some point, it would just sort the samples in order, and we'll just start trying different splits for each value. So at the end, the number of splits in a continuous variable is infinite, but the number of values is finite. So at the end, we have a finite number of a split we want to try. So for each split, we're getting the number of one class, the number of the other. Something I didn't mention before, this is nothing really specific. Decision trees deal great with more than two classes for prediction. In this example, I didn't mean because it's complicating things. But if you have three classes like the Iris dataset that we've seen before, it's something that it will manage without any problem. So at the end, this will get, for each of the split, we'll get two different legs. And for each leg, we will know the number of values. For example, in this case, it's a pure node. It's like we split in a way that we have only one sample in one side, that it's an 18-year-old person that didn't come to one of the events. Okay, so having this, we can compute the probability of a person coming to the event, as we see for the second. So what it happens here, as I mentioned, is like for each feature, it checks, and for each value, what it's doing is trying to find this entropy that represents the quality of this split. Okay, so we have this, how those splits are, how those two subsets are how good are they? Oops, sorry. So basically, this is computed with this measure, the entropy. There are some other methods. The default in scikit-learn is Gini, but they are somehow similar. That it's just taking the probability, multiplying by the probability, and at the end, the thing is that it's getting this curve. The meaning of this is that if this value is 0, it means that we are in a pure node. Okay, so all elements are of the same class, so everybody is coming in this specific split. So our impurity to say it would be 0. So the node is already perfect. So in this case, this node is perfect in a way because all the people, there is a 0 here, so it means all the people is false. This is what we want. Even in this case, it's not really good. Of course, there is just one sample. Oh, sorry. So at the end, what we want basically is just to find the ones that are in both sides, whether they are biased towards one class or to the other. But at the end, what we want is just to make sure that we find the nodes as impure as possible. So the split is the best split, that it's what we are trying to find. Okay, in this case, the worst case would be that we have half people on one class, half of the people in the other class in the one. So basically, what it's doing is computing this simple Python code. And at some point, what it's doing, because as we've seen here, there is this split that looks quite good because it's impure. Its impurity would be 0 because it got this this partition without any person that did attend, so we know that this is really what we want. But the thing is that we don't want this split because it's just splitting one sample. So what we do is just weight them. We just make sure that we weight on the numbers, so we are not just making sure that the two nodes that we are splitting are as impure as possible, but that they are somehow relevant, that they have enough values to be worth the split. Okay, this is named the information gain that is not implemented in the model that I mentioned, but basically it's saying at each step, every time that the tree is splitting, how much information, how much entropy we are winning, to say what's the information gain on the discriminant power. So just to conclude, as I mentioned before, these are some other applications of decision trees. Mentioned it briefly, exploratory analysis. Even if you are going to end up using a super vector machine, a deep neural network, whatever, I think it's really useful to just have a decision tree in place just to get a sense of the data. At the end, the plots we've seen are quite useful. Seeing the decision boundaries in a scatter plot, it's great, but it just works with two variables. So it's something that we won't be able to see in most of the problems. But what we can still see, even if we have 10,000 variables, is the tree. The tree, the picture of the tree, the leaves is something that we can see. And as I mentioned, even with 1 million or 10 million rows in our data, the trees are still useful, and they still can be seen. I mean, even if you are not able, if you end up with a tree with 10,000 leaves, you can still see like the 3 first levels. It's something really, really easy to see, and it provides you a lot of information on how important is it. Another thing we didn't see in detail is the probability estimation. We've seen how to classify. It's at the end. We've seen that if you end up in a pure node, you know exactly which class. In the case it's not a pure node, I mean, there is 3 people who came, and there is just one that didn't. We can extract the frequency that basically is a probability. It's a good heuristic for probabilities. If we compare it to the logistic regression as before, logistic regression also, if you check scikit-learn, you can extract the probabilities from your model. But at the end, the probabilities are just the distance from your element to the boundary, to the decision boundary. So it's something that at some point you can use a sigmoid function, and as in the logistic regression, and you will end up with a number between 0 and 1, and will look like a probability. But at the end, it's more a confidence. It's not a proper probability in being technically accurate, to say. So I think for probabilities, and especially if you have a lot of data and you can really have one of your nodes, one of your leaf nodes with 1,000 rows, 1 million rows, it's like, okay, you know that when this specific case happened in your problem, you know that this was the frequency, so you know the empirical probability of it. Also, we can use it for regression. The idea is more or less the same. We start splitting. For each split, we get the average, to say, and we give it as the value for the regression. There are also more advanced methods that basically fit a linear regression in each of the splits. That something can be done. I think it's probably quite expensive in computational terms. So takeaways, it's like, as we've seen, different approach. It's not like following a linear equation. It's not doing matrix multiplication. It's something different. You've seen it's quite straightforward. As we've seen, we just go over the tree, just getting the best split. The best split is just the entropy. We've seen nothing of this is really complex. We've seen that it can be used for different things. There are some strong points. The best one, depending on the problem especially, it's not a black box. It's just a model that we can understand and we can debug. We can see why it's behaving like this, that in many, many real problems is something key, is something that our manager might not let us use a model if it's a black box in some cases, because we need to be able to know, to explain a customer, to explain a senior manager why we made a decision or a model made a decision. There is some implicit preprocessing. Some of the weak points, it overfits. We need to control it. The performance can be bad, but as said, I think this shouldn't be an issue. And we need also to take care of feature extractions and binding to make sure that we can get the most of the model. So that's it. Thank you very much.